Hey guys, today I'm going to be doing a little video on the difference between strong and weak acids with this little example I made. So let's just get straight into it. So first we have disassociation. One of the biggest differences between strong acids and weak acids is their disassociation, or their interchangeably used ionization, meaning that a stronger acid almost completely disassociates at equilibrium. So let's say you have an acid right here. This is our acid. Now, as it approaches equilibrium, your acid splits into the conjugate base, the conjugate acid and the conjugate base, as we can see, right? They're almost completely disassociated. If this was drawn to scale, you'd probably see like maybe one molecule here, depending on what the acid is. But in general, strong acids almost completely 100% ionize. Okay, now it's not the same for a weak acid. For a weak acid, most of the acid is actually present as equilibrium. So we have our acid number B, and as this acid approaches equilibrium, it actually doesn't dissociate that much. Once again, the values of dissociation are dependent. They vary based on the acid, but the general idea for weak acids is that they do not, they're nothing like a strong acid in their dissociation. So here for HB. And this is what it probably looks like. There's maybe one disassociated, right? So how I like to an example I like to think of this is I like to compare let's say HCl to any sort of acid with an organic background, and there's an actual name for these acids with the organic background. They're called the ones that commonly contain a carboxyl group. So let's say acetic acid, like HC2H3O2. Remainder of these, they don't dissociate. And what people get confused about is they're like, well, okay, so we have our acetic acid, right? So there's two ways to write it. I'm just going to write it the way where you can see the formula, C2H3O2. This is one acidic hydrogen, but the remaining hydrogens in these molecules are not acidic. They're not acidic. This is not like a diproctic or a whatever you want to call it. This is not one of those. This is not like H2SO4, in which there are two acidic protons. So I thought that was something interesting to note. Okay, moving on to conjugate bases. A strong acid yields a weak conjugate base. This is very, 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 very important. So a weak conjugate base, meaning one that has a low affinity for a proton. And it can also be described as one whose base is much weaker than water. In this case, the water molecules are winning in quotations, winning the competition for the H+ ions. Now, a weak acid is inverse, literally the inverse. A weak acid yields a strong conjugate base with a high affinity for a proton, and it is a much stronger base than the water, meaning that here the conjugate base is sort of winning the H+ ion, or you can think of it as the water is not successful in pulling these H+ ions from the base. The weaker the acid, the stronger its conjugate base, and the various ways of describing acids can be described on tables, or however you want to rationalize it. This is just how I think of it, like an inverse relationship. Okay, equilibrium. So as we can see, equilibrium and disassociation go hand in hand. So a strong acid's equilibrium is going to lie far to the right. Now, let's look at it like this. Excuse me. Far to the right, almost completely disassociated. And we just stated that a strong acid almost completely disassociates. So here we go. You see the connection, right? Okay. Now, a weak acid, again, wants the inverse. The equilibrium lies far to the left here because most of the acid is present at the equilibrium. It's not breaking apart. It doesn't want to break apart. And there's actually a reason behind this. I can get into that. There's a reason that the weak acids don't want to break apart. It's because of the molecule, and it's the way that the molecule is formed. But we'll get into that later. Okay, now examples of strong and weak acids. So there are different types of strong and weak acids. There are also some that aren't mentioned on here, like oxyacids, which is just when an acidic proton is attached to an oxygen atom. You'll see this a lot, and being an oxyacid doesn't mean you're necessarily strong or weak. You can be either, but For strong acids, a monoprotic acid is a strong acid. A strong monoprotic acid is an acid with one acidic proton. So HCl is a great example. Very strong, one acidic proton. A diprotic is one with two acidic protons, as we see, H2SO4. And then the inverse is just a weak one, like HNO2 with one acidic proton, whoa, and H2CO3 with two acidic protons. That is really the summary of strong versus weak acids. And if you get really good with this, the rest of the chapter is sort of like it makes sense. It conjugates in your brain.